Okay, so imagine this for a second. You're holding your phone. You're about to take a selfie. But there's a catch.
Right.
You are not in your bathroom. You are speeding through the universe at, say, 50% the speed of light.
In some kind of futuristic car or spaceship, doesn't matter.
Exactly. And you look into a mirror that's moving right along with you. Maybe it's on the dashboard. You snap the picture. What do you see?
Well, you ask Albert Einstein if you consult standard relativity. The answer is genuinely pretty disturbing.
Uh-huh.
Because of that speed, the physics predicts your face in that reflection would be physically warped, squished, stretched.
Literally shaped like a banana.
Literally a banana.
And just to be clear, because I think this is where it gets confusing for people, relativity isn't saying that's a camera glitch, is it? It's saying your face actually is that shape.
That is the standard interpretation, yes. Space itself is crunched up,
Right.
length contraction kicks in. So the object, your face, is physically deformed in that frame of reference. The universe bends, and you bend with it.
Okay, hold that image in your head, a banana face. Because today, we're diving into a whole stack of documents that challenges that idea head on.
Completely.
We're looking at a new physical model. They're calling it the Zionod-Chat view that says, no, your face is fine.
The banana shape is just an optical illusion. It's caused by signal lag.
It's a bold claim. It's basically saying we've been confusing the map with the territory for 100 years.
A very bold claim.
And we have a fascinating stack of sources to look at today. We're not just talking philosophy. We've got technical papers. We have actual Python code for a 3D simulator called the Banana Face Relativity Simulator.
Which has to be the best name for code ever.
It's incredible. And we even have transcripts of AI auditors.
Yeah, that part is wild. They brought in Gemini and Claude to act as space-time auditors.
And these AI auditors came back with, well, a pretty surprising verdict. They called this new perspective logically complete, even revolutionary.
Which, is not something you typically hear when you try to argue with Einstein.
Not at all. So, are we living in a bendy universe where my face turns into fruit at high speeds? Or are we just looking at a very laggy picture? That is the mission for today's deep dive.
Okay, so to understand this, you have to start with their foundation. The source material is very, very strict about separating reality into three distinct worlds.
The three worlds. All right, I saw this in their background knowledge PDF. It almost felt like they were laying down the law before we could even talk physics. Why is that separation so important to them?
Because if you mix them up, that's where you get the paradoxes. You get magic. You get all the confusion.
Okay.
So let's break them down. World one is the mathematical world. Pure logic, formulas, geometry. It's where the Lorentz transformations live. It's perfect, but it's abstract.
Just numbers on a page.
Right. It describes things, but it isn't the thing itself.
Yeah.
Then you have world two, the physical world. This is the territory. The source describes this as the actual electromagnetic field, the medium. Real events happen here. If a light flashes, it flashes here. This is, objective reality. It doesn't care if you're looking.
And the third one, this is where the trouble starts.
This is where the trouble starts, the observational world. This is the map. This is the data we collect from light signals. And here is the key, the absolute key to this whole thing. Because light takes time to travel, this world is always delayed. It's always old news.
So the core argument of this new model is that Einstein's relativity takes world 3, the old laggy news, and mistakes it for world 2, the actual territory.
Precisely. The sources use a really punchy term for this. They call it description narcissism.
I loved that phrase, description narcissism.
It sounds like a psychological diagnosis for a physicist.
It kind of is. The idea is this. Einstein correctly realized that light takes time to reach a moving observer. So if I'm moving away from a clock, the light takes longer to catch up to me, so the clock looks like it's ticking slower. Sure, that's time dilation. We've all seen Interstellar. It's a sci-fi staple.
But instead of saying, oh, I'm seeing an old, distorted image because of signal lag, standard relativity concludes the universe itself must have changed. Time itself has slowed down.
So because my view is laggy, the universe must be warped. That's the narcissism. The universe changes just to accommodate my bad viewing angle.
Exactly. The source material uses a great metaphor here. It's like looking into a funhouse mirror.
Okay, yeah. The ones that make you look all tall and wiggly.
Right. If you have a perfect mathematical formula, that's world one. The math, you can predict exactly how the mirror will distort your reflection. The math works perfectly.
Sure.
But if you start believing your actual bones have stretched out to look like that, You've made a huge category error.
You've confused the distorted map with the solid territory. You think your legs are actually 6 feet long because the mirror shows them that way.
And this model argues that for the last 100 years, physics has been panicking about our bones stretching when we should have just been laughing at the mirror.
Okay, that is a huge claim. But if we're not using Einstein's relativity, what are we using? The documents describe a setup, a rig to prove this point. It involves a boss and something called a point cloud.
Yes. This is where we get into their realist view. So imagine an absolute electromagnetic field. Think of it like a giant invisible ocean, a canvas. This is the territory, and it's just sitting there, stationary.
And high above this is the boss.
The boss observer.
Yeah.
In the simulation code, the boss is at coordinates 0, 0, 100. The boss is completely static relative to this field. He's not moving. So he sees everything exactly when it happens once you correct for light travel time to him.
He has the God's eye view, the ultimate referee.
Exactly. And down on the field, we have our actors, a train on a track and a car on a road moving parallel to it.
Okay, so what is this point cloud concept? That sounds abstract.
It's the crucial part. In standard physics, we think of objects as continuous things. But this model says, no, reality, or at least how we track light, is a four-dimensional point cloud.
What does that mean in practice?
It's a way of tracking. So imagine a passenger on that moving train turns on a flashlight for just a split second, a single pulse.
Okay. A flash. One event.
Where does that light start? Now, standard relativity says the light inherits the train's motion. It travels with the train. But this model uses something they call the pin analogy.
The pin analogy, I found this part really interesting.
Yeah, it's a good one. If a passenger on a train drops a pin out the window, does that pin stay with the train?
No, of course not. It hits the ground. It stays on the tracks.
Exactly. This model says light works the same way. When an event happens, like a flash, it is pinned to that coordinate in the electromagnetic medium. The light spreads out from that spot on the tracks. It doesn't care that the train has moved on.
So the train literally leaves its own light behind.
The source of the light, the bulb, moves with the train. But the emission point, the exact spot in space where the light was born, that stays fixed in the medium.
Let me make sure I'm getting this because it feels critical. If I'm on a train and I flash a light, standard physics says the center of that light bubble moves with me. The Zionad model says, no, I flash the light and I immediately drive out of the center of my own light bubble.
That's it. You are leaving the emission point behind you. And that one distinction, that is what causes the banana phase.
Okay, let's finally get to the banana. This takes us right to the core experiment, the one they coded up in the Blender simulation. The banana face paradox.
Right. Let's set the scene. You're in a car, speeding down a road. Next to you on a parallel track is a mirror moving at the exact same speed. And you want to take a picture of your own reflection.
Sounds simple. I'm moving, the mirror's moving, but we're moving together. In my intuition or Galileo's world, nothing should look weird. It's like taking a selfie in a moving airplane. You don't look distorted.
It feels that way. But light isn't infinitely fast. And in this scenario, you are moving very fast, let's say half the speed of light.
So I'm trying to take a picture. Light has to leave my face, hit the mirror, and come back.
But remember the pin analogy. It's not a straight shot anymore. The documents call this deviation shooting.
Deviation shooting, like leading a target in a video game.
Precisely. Think about the geometry of it. Light leaves your nose, it heads for the mirror. But by the time that light gets to where the mirror was a moment ago, the mirror has moved on. It's further down the track.
So the light just misses it.
If you aim straight at it, yes. So for the light to actually hit the moving mirror, it has to take a diagonal path forward, has to chase the mirror.
Okay, so it has to angle forward to catch up to the mirror.
Then it bounces off. But now it has to hit your camera lens. And your camera is in your car, which is also moving at half the speed of light. So now the reflection has to chase you down the road to catch up to your lens.
Wow, so the light from my nose goes on this long zigzag journey through space just to get back to me. It's doing a lot of work.
A lot of work. Now think about the light from your ear. Your ear is a few inches behind your nose, maybe.
Right, a slightly different starting position.
That slight difference in position means the light from your ear has a different travel distance to the mirror and back. The zigzag has a slightly different geometry.
Oh, I think I see where this is going. If the travel times are different.
Then the light from your nose and the light from your ear that arrive at your camera at the exact same instant must have left your face at different times.
Whoa. Okay, let me get that straight. The camera shutter clicks at time 0. It catches a photon from my nose, and a photon from my ear. But because of the zigzagging, the nose photon might be, say, 1.0 second old, but the ear photon might be 1.2 seconds old.
Exactly. You are seeing a mosaic image. You're seeing your nose as it was 1 second ago, and your ear as it was 1.2 seconds ago. And because your car was in different positions at those two different times.
The parts of my face appear to be in different places in space.
It smears the image, it stretches it creates a curve, banana shape.
So the banana face is real then. It actually shows up on the camera.
Yes. The image is a banana. The observation is a banana. If you developed that photo, you would see a banana. But here's the revolutionary part. The Zion chat model says your face is still round.
But the data retrieval was curved.
The data retrieval was curved. Standard relativity looks at that photo and says, see? At high speeds, objects physically deform. Your face is a banana.
That's that description narcissism again. Mistaking the laggy photo for the actual thing.
Precisely. And the source code they included actually creates something they call a ghost ring to visualize this.
I saw that in the Python script. It renders a pink ring and a blue ring. What do those represent?
So the code uses a technique called reverse ray tracing. It starts at the camera and works backward in time. The pink ring is the simulation of the light particles arriving. That's the distorted banana face you see. It's warped.
And the blue ring.
The blue ghost ring shows where the face actually was in the medium at that moment. The simulation shows them both at the same time to prove the point. The distortion is an artifact of the method, not a fact of the object. The blue ring is perfect. The pink ring is a mess.
It's amazing they built a whole simulator for this. It's not just a thought experiment. They did the math. They coded the actual light paths.
And that math led them to a really interesting critique of how we govern physics. They compare an inertial frame, which is the standard tool in relativity, to a modern nation state.
Yeah, that metaphor was unexpected. A nation state. How does physics relate to politics?
Well, think about what a country does. It establishes a standard time, Eastern Standard Time. Everyone in that zone agrees it's 12:00 p.m.
Right. We synchronize our watches so society can function.
But in physical reality, if you and I are standing a mile apart and lightning strikes, I hear the thunder at a different time than you do. My now is different from your now because of the signal delay.
Sure, that's just basic physics. Sound takes time to travel.
A nation state, or an inertial frame in physics, tries to smooth all that over. It forces a democracy of time. It averages everything out so we can all agree on the coordinates. It says, let's just pretend the lightning happened at the same time for everyone.
Which sounds helpful, right? We need to agree on time for GPS to work.
It's helpful for making train schedules, for sure.
Yeah.
But the source argues that when you do this in fundamental physics, you are committing what they call the destruction of physical quantities.
That sounds bad. What are we destroying?
We're destroying the actual history of the photon. By averaging things into an inertial frame, you delete the raw data of how long that specific particle of light actually traveled. You replace the messy, real point cloud of arrivals with a smooth, mathematical fiction.
So we're trading truth for convenience. We're smoothing out the banana shape with math and pretending it never happened.
Or worse, we're accepting the banana shape as reality because our democratic frame says so. The source argues this convenience is what creates the paradoxes. By ignoring the individual lag of every single pixel, every citizen in the metaphor, we create a model where time itself has to warp to make the math work.
Instead of just admitting, hey, some citizens got the news later than others.
Exactly. The Zion chat model says, abandon the democracy. Go back to the boss's eye view. Track every single particle relative to the absolute medium. And if you do that, there is no time dilation, there is no length contraction, there is just light taking a long time to hit a moving target.
It seems so simple when you put it that way, just track the light. But this goes against 100 years of accepted science. Did they really run this by AI? I mean, usually AI just recites the textbook.
They did, and that's what makes this so fascinating. The sources include actual logs from these space-time auditors.
Gemini and Claude specifically.
Right. They didn't just ask general questions, they fed this specific logic. The three worlds, the banana face geometry, the Python code, into these models. And they asked them to act as unbiased auditors.
So they said, don't just tell me what Einstein said, check the logic of this model.
Exactly. Does the point cloud concept resolve the paradox?
And what was the verdict? Did the AI just glitch out?
No, it admitted the logic is logically complete. Gemini specifically called it a revolutionary perspective.
Revolutionary, that's a strong word for an AI. They're usually pretty conservative with their language.
The AI acknowledged that if you accept the core premise, this absolute medium, world 2, then the paradoxes of relativity do in fact disappear. It validated that the banana effect can be fully explained as an optical illusion. You don't need to warp space-time.
That's a big deal. It means the math holds up. Even if you disagree with the premise, the internal logic is sound.
It is. The AI recognized that standard relativity is inside out. It builds the universe from the observer's limited view. This model is outside in. It builds the view from the universe's objective reality.
It's the difference between drawing a map from the ground while you're hiking versus looking at the satellite footage.
That is a perfect analogy. The satellite footage, the boss's view, it doesn't have the distortions the hiker on the ground sees. The hiker sees a curved path because of a hill, but the satellite sees a straight line.
Okay, so let's recap. We have a simulator that produces a banana face without warping space. We have AI auditors signing off on the logic. And we have this point cloud concept that just tracks events on a static canvas.
It forces you to ask a really uncomfortable question about modern physics.
Yeah.
Have we been making things so complicated, inventing time travel and wormholes and warping space, because we refuse to accept that our view is just slow?
It really shifts the power dynamic. In relativity, the observer is king. The universe literally bends around me. If I move fast, the universe shrinks for me. In this model, the universe is solid, and I'm just a guy with a slow camera trying to keep up.
It's a shift from narcissism to realism. And it suggests that the math of relativity, as useful as it is for prediction, might just be a really, really good formula for a funhouse mirror. It predicts the distortion perfectly.
But it doesn't describe the bones.
It doesn't describe the bones.
Which brings us right back to that question from the source. If you look in a mirror and your reflection looks squashed,
do you panic and rush to the hospital because your bones are broken? Or do you just realize the mirror is curved?
And physics might have been rushing to the hospital for 100 years, prescribing space-time surgery, when all we really needed was a better understanding of optics.
It's certainly a possibility worth simulating. And the fact that we can model it in Python and get the exact same visual results as relativity, but with a completely different explanation, it suggests it's not just philosophy, it's a viable geometrical alternative.
This has been a really mind-bending look at the Zionaut chat model, a reminder that sometimes the biggest breakthroughs come from just looking at the raw data and questioning the map we've all been handed.
Always check the territory.
Thanks for diving deep with us today. Check your mirrors, don't trust the lag, and we'll see you on the next one.